So one question that you can ask, which is an interesting question, is when we did this result for the DIS, we got this convolution between the hard function and the Photon distribution function. And you can ask, why did that happen? And in general, is there a way of characterizing when it could possibly happen? Because if you think about the answer that we got, it was just Wilson coefficient times operator. And the really only non-trivial thing about it was that there was this one momentum that could kind of trade back and forth between them. There was an integral in the answer. And actually, power counting even constrains how those integrals can in general show up. So if you ask kind of most generally what could possibly happen, then just thinking about the power counting for the degrees of freedom actually tells us what type of integrals can show up in factorization theorems. This is constrained by power counting. I keep forgetting to say that there's a makeup lecture tomorrow. I sent around an email, but I should. Tomorrow, this room at 10 a.m. And their lecture next week is canceled on Tuesday. That's why we have a makeup lecture tomorrow. OK, so in what way is it constrained by power counting? So if you think about the degrees of freedom that we had, say for SCT1, then we had hard, linear, and soft. So let's just take a simple case with only one type of linear, hard, linear, and ultrasoft. And the p mu of these guys in terms of plus, minus, and perp components should be more fancy about this. Write it. So if you think about just the power counting for the momentum, it was as follows. Factorization was separating these different things into different objects. We had a Wilson coefficient for the hard. In the case we just did, we only had a proton matrix element for the linear. We didn't have any ultrasofts. If we put the ultrasofts in, they would have all canceled away. We wouldn't have seen any ultrasoft showing up. And that's because the operator we were dealing with, the Wilson lines, would just have canceled completely out of it. But actually, it turns out for deep and elastic scattering that you shouldn't even include ultrasofts. They're not a good degree of freedom to include there. So really, for the process that we were talking about, you really should only take those two. OK, but anyway, more generally in some other process, you would have these three different things. And the way that convolutions can show up is simply who can trade momentum with who. OK, so this is plus momenta, minus momentum, and perp momentum. And in order for momentum to be exchanged, they have to be of the same size. So these guys here are the same size, and they can be exchanged. And that's exactly what showed up in our DIS factorization theorem. The hard Wilson coefficients exchanged minus momentum with the linear modes because they are the same order in the power counting. In another case, in a more general, or in some other example, we might find that there was non-trivial ultrasoft stuff, and then we could get a convolution in the plus momentum and the linear and ultrasoft because they're the same size. And so that's pretty simple a way of thinking about why those integrals can possibly show up. It's just because the two sectors can talk to each other because they have momenta that are the same size. And then the rest is about momentum conservation, because momentum conservation places non-trivial constraints. And we saw in the DIS example that there was 2 omegas to start, but one of them was projected to 0 because it was forward matrix element. We only had one integral. And that also has analogs elsewhere. If we do SCT2, which we haven't talked about yet, we did talk about what the degrees of freedom were. And again, if I try to make it completely generic for some examples that we'll treat later, then I can write down something that's a slightly extended version of what we talked about so far. So I can have Q, Q, Q again for the hard. And then I can have my collinear, which is Q lambda squared, Q, Q lambda, and then soft, which is Q lambda, Q lambda, Q lambda. And it turns out that sometimes there's also another mode, which we haven't talked about, but kind of include it for completeness. Which is kind of in a collinear mode that's in between the low energy collinear mode and the high energy collinear mode. Yeah. Square root of lambda, sorry. Yeah. Otherwise, my dimensions are wrong. Nice. Yeah. So again, here you can just, I mean, the reason I was extending this is just to, again, argue that it's kind of simple to see what can happen. So in general, when you think about convolutions in the hard momentum, it could be, in this case, between these three modes. There could be some integrals. And then you can look where else there can be something. So this and this are the same size. And this are the same size. So in general, those things can involve, we can have convolutions in general between all these things, between the guys that are the same size. But that's the most complicated thing that can happen. It can't be more complicated than that. And you see that in some examples, you either have the purple or the orange, but not both. That's kind of typical that you don't get the most complicated thing. OK? So when you have results for observables that tell you how these things couple together, those are called factorization theorems. And in the effective theory, because you sort of define the modes, separated them at the start, you're kind of very quickly getting to these factorization theorems. OK. Yeah, let's see. So we're going to deal with a bunch of different examples. And I've decided that I'm going to do it in the following order. So we're going to do the next example. So we're going to do a bunch of examples in order to sort of see kind of the range of possibilities that can happen. And so I'm going to stick with SCT1 for next lecture. So the next example we'll do, which I'll call example 1, is we'll do our dijet production. So this is a SCT1 situation. And the difference between the example, so far what we did is we did DIS. DIS, was so simple because it only had 2 degrees of freedom that you could kind of either think of it as SCT1 or SCT2. I mean, technically it's more like SCT2, but it behaves like SCT1. There's no ultrasofts. Remember, it's ultrasofts and softs that are kind of making the distinction between the two. So if you just have this mode and this mode, there's not really any difference between calling it SCT1 or SCT2, so it's just SCT. So E plus E minus to dijets will be an SCT1 example, which has ultrasofts. And actually, what we'll find in this case is that it will be the purple. We'll get a purple convolution. We'll see how that happens. And we won't actually, momentum conservation will rule out the possibility of the orange one. OK, so we'll see kind of the opposite situation where it could be that we have ultrasoft modes as well, but then we only get a convolution with those ultrasoft in the factorization theorem and not with the clinic and the hard. And then we'll turn to SCT2. And I haven't totally decided what processes I'll do, but I think I'll do the following ones. So one thing that you can do, which is pretty simple, is to look at something called the photon-pion form factor. So real photon to pion transition through another virtual photon, which you can think of as happening through a diagram like this with 2 quarks. one of them that's off shell and one of them that's on shell. This is a pi 0. So this is an SCT2 example, but again, it's pretty simple because it's just going to involve one hadronic object, and actually it will just, in this case, have collinear modes. Pion will be, we can set things up so the pion is n collinear, and then we have hard modes. So that's one example we'll do. Another example we'll do is b to d pi. And here the b and the d are soft. Remember, we talked about this one, and the pion is collinear. And then we have hard modes. So this is kind of like, in some sense, a DIS, but it's an exclusive process, not an inclusive one. And so actually all the tools that we use, which were kind of, in DIS, it's the most inclusive process you can think of. It's deep and elastic scattering. The I is for inclusive. Here we're doing something completely exclusive. But we'll see that all the things that we've been thinking about, which is just separation of collinear modes and hard modes, we'll just go through for that process too. Okay, so the effective theory, the difference is that in this case, you will not be taking the amplitude squared. You won't be looking at forward scattering. The forward scattering was what was making it inclusive. We were summing over all the final states. Here there's only one final state. So the difference between this example and the one we just did is that in this case, we'll factor the amplitude. Not the squared amplitude. Okay, but other than that, it'll look very similar to the example that we did for DIS. B to d pi then is an SCT2 example where we make things a little more complicated because now we have soft, collinear, and hard modes. And we'll see what happens there. And then I'll do some more examples after that. But so we'll do some LHC examples. And I think we'll also do broadening. Okay, which is another E plus E minus observable. All right, so that's where we're going. And we'll start going there next time by talking about dijets in Scat 1.